Hello friends. Imagine standing between two mirrors. Each reflection shows another reflection, and another, going on forever. Now imagine a function that works the same way. It calls itself, and then that copy calls itself again. And again. If you have ever seen code like that and thought, wait, how does this ever stop? Or what is actually happening inside the computer when this runs? You are in exactly the right place. In this video, we are going to pull back the curtain on recursion, trace exactly how the call stack grows and then unwinds, and build a mental model you will carry into every recursive problem you ever solve. Let's start with the simplest possible question. What is recursion, really? Recursion is when a function solves a problem by calling a smaller version of the same problem. That is the whole idea. You take something too big to solve directly, you peel off one piece, and you hand the rest back to the same function. Each call works on something slightly simpler than the one before it. Think of it like a set of nesting dolls. You open the biggest one and find a slightly smaller one inside. You open that and find an even smaller one. Eventually you hit the tiniest doll, the one with nothing inside, and that is where the work actually finishes. The key insight is that every call is a fresh, independent copy of the function working on its own smaller piece of the problem. Now for this to work safely, every recursive function needs exactly two things. Let me show you what those are. Every recursive function is built from exactly two parts, and you cannot skip either one. The first is the base case. This is the stopping condition, the simplest version of the problem that you can answer directly without making another call. The second is the recursive case. This is where the function calls itself, but always with a simpler input, moving one step closer to the base case. The base case stops the recursion. The recursive case drives it forward. If the base case is missing, the function calls itself forever, and the program crashes. If the recursive case never gets simpler, same result. Throughout this video, we will use the factorial function as our example, because it is clean, predictable, and makes both rules very easy to see. Let's look at the code and then trace what happens inside the computer when we actually run it. Here is the factorial function. The base case on line 3 says, if n is equal to 1, return 1 directly. The recursive case on line 5 says, return n multiplied by factorial of n minus 1. Now let's call factorial of 4 and watch the call stack grow. The computer cannot complete factorial of 4 yet because it needs factorial of 3 first. So it pauses and pushes a new frame onto the stack. That frame calls factorial of 3, which needs factorial of 2, which needs factorial of 1. Each paused call waits on the stack, holding its own value of n. When we finally reach n equal to 1, the base case fires, and we get a real answer back. The stack has 4 frames now, and nothing has multiplied yet. That all happens on the way back up. Now the stack unwinds. Factorial of 1 hits the base case and returns 1 to the frame above it. Factorial of 2 was waiting with n equal to 2, so it computes 2, multiplied by 1, and returns 2. Factorial of 3 was waiting with n equal to 3, so it computes 3 multiplied by 2, and returns 6. Finally, factorial of 4 was waiting with n equal to 4, so it computes 4 multiplied by 6, and returns 24. That is the answer. Each frame resumes right where it paused, uses the value it just received, finishes its own multiplication, and hands the result to the frame above. The stack shrinks one frame at a time until it is completely empty, and factorial of 4 has its final value of 24. The build-up and the unwind together are the full story of how recursion actually executes. Let's wrap it all up. Alright, let's bring it all together. Every recursive function works in two phases. On the way down, each call pushes a new frame onto the call stack, pauses, and waits. On the way back up, each frame resumes, finishes its calculation, and returns a value to the frame that called it. The base case is what starts the unwind. That mental model works for factorial, for tree traversal, for any recursive algorithm you will ever write. Now here is the watch out. If you forget the base case, or if your recursive case never actually gets simpler, the stack keeps growing without end. Eventually the program runs out of memory and crashes. That error even has a name, stack overflow. Always ask yourself, does every possible input eventually reach the base case? If yes, you are safe. Thanks for watching, friends. Now go write something recursive.